So we're going to talk about some more tests for proving series converge or diverge. And we're going to learn 2 more tests today, and they're called the comparison tests. And the basic idea here is that you compare your series to something that you know something about. And 2 common series you know stuff about are geometric series. You know when those converge, right? And p-series are super easy things to compare to as well, okay? So like, look at this guy. Do you think this should converge or diverge? Like, it looks almost like something that you know, right?
It'll converge, right?
Yeah, this looks like super close to the sum from n equals 1 to infinity of just 1 over 2 to the n, right? Pretty much, which is a geometric series. With r equal to a half, right? And therefore it converges. Does that make sense? But you can't say it's a geometric series because of the whole, it being the first one, because of the whole plus 1 in the denominator. That makes it not geometric. Geometric just means something raised to a power times a constant. So, but the point is it's kind of close to a geometric. And actually, if you were looking at 1 over 2 to the n plus 1 relative to 1 over 2 to the n, who's bigger? The one on the right side's bigger, isn't it? Do you buy that? When you make the denominator bigger, the fraction becomes smaller, yes? Okay. So, I mean, that also suggests that you have something that's less than a series that's converging, so probably it could converge too, right? And that's kind of what the direct comparison test says, and that's the following thing. Okay. So suppose you have series with positive terms. So that's the only assumption you have to have for this test. And officially, the book says positive. It's okay if terms are 0. Like, the book doesn't really go there, but it's totally fine if your terms actually are 0, because adding 0 to something doesn't change the sum, right? Okay. Now, if this relationship is true, if you have the a sub n's are less than or equal to the b sub n's for all n's. So supposing you know that b sub n converges, do you buy that that implies that a sub n converges? Because what this is kind of saying is if the bigger series converges, so does the smaller. Does that idea make sense? We kind of used a similar thing for the integral test proof, didn't we? Except for it was a series and an integral that we were comparing to each other, right?
So it's like the squeeze theorem?
It kind of is like the squeeze theorem, yep. But except for the squeeze theorem tells you what something converges to exactly, this thing just tells you that it converges.
Right.
Does that make sense? But the squeeze theorem gives you a specific value, but it is also kind of squished, which means it's finite.
Right.
If a sub n diverges, then b sub n diverges. So in this case, you see how the a sub n and b sub n flipped? But that's because for this implication to happen, you have the smaller one diverges, means the one that's even bigger than it has to diverge to, right? Which makes sense. So if the smaller series diverges, so does the larger.
So if you ever get it to where somehow you're getting the smaller one diverges, but the bigger one converges, then someone's lying to you about something?
Yes, if the smaller one diverges, the bigger one absolutely has to diverge,
Okay.
without a doubt. But if the bigger one diverges, you can say nothing about the smaller one. Does that make sense? It just doesn't tell you anything.
Okay.
So you have to have the inequalities going the right direction to draw conclusions from this test. And so the hardest thing to do is to make sure that your inequalities go the right way. Okay, that's the trickiest thing here. We're going to technically just do a little bit of a proof of why this works. So let's start with just the first one. Let's call that one A, and let's call this one B. Okay, so remember, a series sum A sub n converges if the sequence of partial sums S sub n, which is the thing that when you do A1 up to AN. Like that's how you show a series converges. You show the sequence of things you get when you add up more and more and more and more terms in your series converges. That's like the definition. Okay, and to prove this, we're going to use that monotonic sequence theorem. And this says that a sequence S sub n, let me say it right, which is bounded and monotonic converges. Do you remember what monotonic meant? That in this case, we're going to be monotonic increasing, either going up or staying the same, okay? Okay, so let's do bounded. How do you know, I have my research today, I didn't look, it wasn't huge. How do you know that this whole sum from I equals 1 to infinity of A sub n is bounded? What tells you that that's true?
As the bigger one.
Because the bigger one converges, okay? So that's bounded, and the reason is because the sum of B sub n converges to some number. You don't know what number, but it converges.
You put 1 equals 1? Do you mean n equals 1?
I meant n equals 1. I'm sorry, my statistics class, they use i's sometimes, and so I'm just having to go back and forth. Okay, and I probably should in here, right, I'm going to put what I'm going to add in purple. We also probably needed to assume that 0 was less than A sub n, less than or equal to B sub n at that stage. Like, assume we had the right conditions met. But the point is that, and this infinite sum, or you could have said your sequence is bounded. How do you know it's increasing? By it, I should also not say it. How do you know that this sequence of partial sums, Sn, is increasing? In other words, like suppose you look at An. An is not A1. God, crap, I'm so sorry. Look at Sn, which is adding the first n things, and Sn plus 1. What is if Sn is adding the first n things, what is Sn plus 1? Adding one more term, right? So all the same stuff. What thing that you assumed about the A sub n's allows you to say thing on left is less than thing on right?
A sub n has to be less than A sub n plus 1.
Not even that. What kind of number is A sub n plus 1? Positive or negative?
Positive.
It's positive. So if you add
Just adding a positive number.
because this is positive, that means that this has to happen, right? And if you want to say it could be 0, well, that'd be greater than or equal to 0, right? At worst, you add it on 0. So thus, your S sub n is increasing. And that's why the positive assumption is necessary, so that you can have the sequence being increasing. If the sequence is not, if the partial sums, the sequence is not increasing, you can't make the conclusion that we're going to make. So since S sub n is increasing, plus bounded, that implies your sequence of partial sums Sn converges, which implies your sum converges. Once we've gotten through all the tests, I think Jill and I should put our heads together before this and make a little cheat sheet for you that says like test, and then have you fill in like what the test does and like what the assumptions of the test are, so you can like keep them straight, because there are a lot of them. Or you could also go through your notes and like make yourself a little list of, okay, today I learned these tests, here are the assumptions of those tests. On the quiz you're going to take next week, I'll just tell you, like, when you're asked to use, we're going to ask you to use specific tests, and then part A is like state the conditions of the test. And for some tests, they're easy. This one, positive terms, that's it. Integral test, the function you have must be positive, continuous, and decreasing, right? There'll be one more test called the alternating series test, which assumes that you have a series that flip-flops positive, negative terms, and the flip-flopping is necessary. So, anyhow, proving divergence is pretty easy, so let's just move on and like talk about an example, okay? So I think in this next one, I'm just going to do A, because I also want to do A really well and like talk about the things we're looking for. Okay, so the first thing you should do, so we'll call this step 1, is explicitly identify AN and BN. Like, I'll write that step down and then we'll do it for this problem. And AN and BN are the terms of the series that you're comparing to each other. Okay?
Doesn't matter which is which.
It only matters in terms of you want the inequality to go the right direction, but as long as you make a true statement with your inequality, you don't have to call AN the first one or the second one.
Alright.
Does that make sense? But the thing we're after in the end is 0 less than AN less than or equal to BN. Okay, but so I kind of like, that's what the relationship in the
Why
test.
does AN have to be greater than 0?
It has to be positive, but it's okay if it's equal to 0 too.
Okay.
If it wasn't positive, like if it was negative, then the whole increasing bit we use to prove convergence wouldn't be true. That's the reason. But 0 is okay. Okay, so before you start, just like kind of like step 0 is do you think the series is going to converge or diverge? Converge. What does it look like? Because if you just ignore the 5, it's 1 over 2 to the n, right? So in my thought bubble, I'm going to compare to 1 over 2 to the n. That's kind of like what you're thinking. Okay. So you want AN to be the smaller one, BN to be the bigger one. So AN's going to be equal to the terms of the series you're given. And BN is 1 over 2 to the n. Okay, second step, show that 0 is less than or equal to AN, which is less than or equal to BN. And don't state, okay? As in, just because you say it's true doesn't mean it's true. It's like politicians. Fact check. I want you to prove to me that it's true.
Well, 0 would obviously be less than all of it, right?
Yeah, we know terms are positive, right? Does that make sense? Because we're doing, so A sub n, B sub n positive. So A sub n certainly is bigger than or equal to 0. That's easy enough, as in, or just state, we have positive terms. Okay, so the way to technically prove that AN is smaller than BN is to start with something pretty obvious. It's pretty obvious that 5 plus 2 to the n is bigger than 2 to the n, right? And then that implies that 1 over 5 plus 2 to the n is less than 1 over 2 to the n, right? So that's the whole, like, showing. Give me something completely obvious that I can believe, and then go from there. Okay. So explain, step 3. And this first one really is A sub n, right? Like that. You wouldn't necessarily have to write the a n and b in there, but that first one was a sub n. So does the inequality go the right way? Do you think? Seems to, yeah. Okay, so explain why the comparing series you chose is convergent or divergent. Okay. So we know the sum from n equals 1 to infinity of 1 over 2 to the n is a convergent what? Convergent what kind of series? Geometric. Does that make sense? Is a convergent geometric series, and then with your r equal to what?
That's actually what I was trying to figure out.
It'd be a half.
But why?
Because you could really have written that as the quantity 1/2 to the n. Because 1 to the n?
I totally thought that was kitten killing that.
No. It's okay. Exponents distribute over addition and division. I didn't just say that. Exponents distribute over multiplication and division, right? But not over addition and subtraction. That's why saying what you distribute over is kind of important. But yeah, 1/2 to the n is the same thing as 1 to the n over 2 to the n, which is, like, that's the
Oh,
That's the
why that
reason,
works.
right? And you use that all the time. Like, if you do 3/4 squared, you know it's 9/16, right? So it's just using that rule, except for in a more abstract sense.
But if it's not 1 on the top, you can't do that, right?
No, because any other number raised to the n wouldn't have that property. But in that case, you probably would have something where you'd have, like, I don't know,
Canceling.
3 over 2 to the n, like it's all there. Does that make sense?
Yeah.
Yeah.
But
And if there was a like if that was like 3 on the top,
you can separate it out.
you could just separate out the 3,
Oh, and then.
right? And then you still have 1/2 to the n. The 3 is part of the a in that case.
But
And
then
that,
you can't technically just distribute over division and multiplication.
as long as you have a ratio or a product raised to a power, that power does distribute over both pieces. I'm not sure if that's what you were asking,
Yeah,
so.
that's what I was asking.
Okay. Yeah, so it's okay for those. All right, and then step 4, last thing is to explicitly make a conclusion. Okay.
Is there a reason you have to do steps 2 and 3 in that order? It seems like you could do it the other way and still get the same answer.
It doesn't matter. Yep, I mean, like, as in if you want, as long as you have all these components here, it doesn't matter what order they're in necessarily. So the conclusion probably should be last, and the a and b should probably be first, right? But you could say, I'm comparing to the sum from n equals 1 to infinity of 1 over 2 to the n, which is a convergent geometric series. Does that make sense? Like, there's lots of ways to say it as long as you include those components.
All right.
Okay, and so your conclusion is, you could say the given series, I just asked Professor Fodry if that was okay, and she said yes. Is convergent by we'll say the direct comparison test.
Is it gonna be like weird indirect comparisons?
Nope, as it is less than a convergent series. Just use the word it.
I feel like B would be pretty easy to look at.
Yeah, and B is, so what do you think B is going to do?
It's divergent because it's greater than 1 over n.
Do you guys agree with him? That,
So the-
let me just show you this is the comparison step. So how is 1 over n minus 2 related to 1 over n?
Greater.
This one's greater, right? And that's because n minus 2 is less than n, right? Which implies that next step, yes?
Yes.
And why did I have to start the series at 3?
Continuity.
The bottom being, the denominator being 0 someplace. And so as the sum 1 over n diverges, that implies sum 1 over n minus 2 diverges. And also you probably could add in like, well, that's definitely bigger than 0, right? It's positive n's. That's like a basic sketch of what that could be, right? The notes online have it done like better. Does that make sense? Yes.
You said no using it, but if you define the subject of the sentence.
It's okay then.
You can use it to.
Yes, if you have said the series in the sentence like earlier, then I think you're referring to that
Like
it.
what you said.
Yes, exactly. Yep, you could have left that as it.
Okay.
I was just being like uber careful about not using it on you
Got, like,
guys.
15 different subjects, then probably specify.
Yes. Okay. Now, sometimes you can't make direct comparison work. And like, here's an example, a couple examples of why can't direct comparison, and Professor Fodry added in the obvious choice. For direct comparison be used to test these series.
Is there a less obvious choice?
Well, you maybe could make it work with something different, as in, but it's not, there's a better way in that case. So what would you want to compare what would you want to compare 1 over 2 plus root n to? Yeah, compare to 1 over root n, right? Because you know that if you sum up 1 over root n, that's going to diverge, right? It's a p series with p equal to 1/2. Okay, but, so 2 plus root n is bigger than root n, right?
Yeah.
Which implies that 1 over 2 plus root n is less than 1 over root n, right?
That tells you nothing.
That tells you nothing. Do you see why? Because this guy, sum 1 over root n is divergent, right? So you have something, and then the sum of 1 over 2 plus root n, I don't know. I mean, you don't know, because the inequality goes the wrong direction, right? To prove divergence, you would have had to have the 1 over 2 plus n bigger than 1 over root n, right? So that's an issue. Bad. Okay. How about this one? Same problem, right? So the comparison here, you want to compare 1 over 2 to the n minus 1 and probably 1 over 2 to the n, right? Does that idea make sense? But 2 to the n minus 1 is less than 2 to the n, right? So that implies 1 over 2 to the n minus 1 is bigger than 1 over 2 to the n, right? The sum 1 over 2 to the n converges, that's for sure. But just because something converges, does it mean something that's bigger than it also converges? No, certainly not. Okay, so the inequality has to go the right direction for that stuff. So when you run into situations like this, the thing to do is not to find something that you think will work, okay, because that's going to be tricky. The thing to do is use a different test called the limit comparison test, which is what we're going to prove next, okay? So this will help you handle those situations. And this lets you use that comparison that is quote-unquote the sort of like obvious thing you would choose right away to make your comparison. So suppose that you have two series with positive terms. If you take the limit of the ratio of their terms, and it's equal to some number c, where c is finite and bigger than 0, then either both series converge or both diverge. So you don't have to, and the benefit to this test is no inequality needed. We prove it using the direct comparison test, like that's what we're gonna do. But when you apply this test, you don't actually have to have any kind of inequality relationship happening. And that's the nice thing. You can just kind of like say, oh, I'm gonna compare it to this thing, and when they get really complicated, you can just go for it. And limits are not so hard to find, right? Hopefully. Okay, why does this work? Okay. So we have some c bigger than 0. And that was assumed that was what was going to come out, right? We can find positive numbers m and capital M so that m is less than c, which is less than capital M. And all this is saying, very general, here's a picture of that. Here's 0, here's your number c. C is some positive thing, right? You can pick some number positive m that's below that c, and some other number positive m that's above that c. Okay, but the point is, if you got a positive number, you can find that your c was 0.5, little m could be 0.4, and big M could be 1. But no matter where your c is, you can find these things. Does that idea make sense? Okay. Here's where you use the limit business. You say, since the limit as n goes to infinity of a sub n over b sub n is equal to c, you can get far enough out so that an over bn is in between that m and that big M. Does that idea make sense? So your limit of this ratio is going to that number c, right? Does that idea make sense? Eventually, if you go to like the 1,000th, 100th, millionth, whatever thing, you're going to have that your ANs over BNs are close to C, right? And if they're close to C, if they're close enough, they're also here, okay? They're also between them. And this is like if N is big enough. And we're going to call that big enough number like capital N or something like that.
The biggest problem is if either of your M's are infinity.
Nope. They can't, you pick them to be finite numbers. So don't pick them to be infinite numbers. Because also, it said that C went to a finite number. So those little m's you pick are definitely finite things. Okay. Okay, so now does this part, this inequality.
Oh, you pick them, not.
Yeah, you pick them, like as in, yeah, you pick some positive little m's.
It didn't just generate.
Nope. Okay, another way to state that is that m times bn is less than an, which is less than capital M times bn. Do you agree with that? How did I get that from the thing I sort of squiggle underlined?
You multiply bn by everything?
And how do I know that won't flip the inequalities?
BN's probably not negative.
Bn is positive, right? That's our assumption of this test. Okay, now focus on this. So this test says that either both series converge or both series diverge. So if your b sub n converges, so does, and what we're going to try to prove here is that b sub n converging implies a sub n converges too, as well, not like the number 2. So if b sub n converges, does number times b sub n converge? Both of those numbers, right?
Yeah.
So does this one, right?
So if like little m was 3 and big M was
10.
9. Right?
Exactly, okay. But the point is, this thing converges, the m times b sub n. So what does that mean about a sub n? Look at this relationship in that box. How is a sub n related to this guy?
It's both larger and smaller than a finite number.
Yeah, but this guy, but the kicker is that it's less than this thing we know is converging, right? And that's the direct comparison test. So that implies that the sum of A sub n also converges. And that's a direct comparison. Why did I choose to use the top one and not the bottom one?
Because you had to divide everything.
If I want to show convergence, do I need to know something about the smaller one or the bigger one?
Bigger one.
Bigger one. That's why I chose the bigger one, right? I want to show this converges, so I look at the bigger one. What's going to happen if you want to show divergence? Just move to a smaller one, yep. So if the B sub n diverges, so does, in both of them really, but so does, the important thing is little m times B sub n, right? So we have that this little guy is diverging, right?
Which means everything else
Which means everything else is diverging too, but most importantly, it means that A sub n is diverging.
So you really chose that one because that was just really easy.
You chose that, the reason you chose the one you chose is because you officially did the direct comparison test. Like both of these statements are by direct comparison. And to apply direct comparison, you have to have the inequality going the direction that you want, or the direction that's needed to make that conclusion.
Yeah, but if you divided by A sub n or somehow flipped it, it wouldn't have been as conveniently.
No,
like
no,
that.
yeah, no, yeah, there is some sort of knowing how this works to explain it to you guys, yeah. Let me say one thing and then you can answer your question, okay? So the one thing I want to say is you don't have to ever do this proof for test. You just have to use the test. So the test just says if you find a limit of a ratio of the terms of two series and it's a finite number, either both series converge or both series diverge. So you don't have to actually do this proof, but the proof of why it works is officially direct comparison. It reduces to that in the end. Yes?
Just a bit small detail, is that supposed to be capital M on the?
No. No, this one definitely supposed to be a lowercase m.
No, the one over it.
This is supposed
In the same signs. If some of these sub n.
No, this was just the regular B sub n. So if the regular series B sub n converges, so does a constant times that series. Nope, so that was just my assumption. I just said, okay, well, if this thing converges, what happens to an? Another one was if bn diverges, what happens to an? But the point is, bn converging meant an converges, right? Bn diverging meant an diverges. They do the same thing. Let's actually do this test on one of them just to show you how it works, okay? Okay. All right, so probably because you have two tests here, well, we'll at some point in time say you're going to use the limit comparison test, okay? Beginning and end, we'll say it at the end. Let's let A sub n be the terms of the series we have, and B sub n be the terms of the series that we're going to compare it to. So what do you think you're going to compare it to? 1 over 3 to the n. Okay, now find the limit as n goes to infinity of an over bn. I'm going to write this out once and then I'm going to be lazy forever, okay? So there's an over bn. Do you agree with that?
Can't you flip the bottom one?
That was the stuff I'm going to be lazy about. Do you guys agree that the denominator is always going to reciprocate? So I'm just going to skip to that step in the future because it just gets tedious to write fractions over fractions repeatedly. So that's equal to the limit as n goes to infinity of 3 to the n over 3 to the n minus 1.
Imagine that the only thing that'd be left there would be the minus 1 at infinity.
Yeah, so is that part okay so far? You could use L'Hopital's rule on this if you wanted to. Or what I'm going to do instead is I'm going to divide the top by 3 to the n and the bottom by 3 to the n.
Still was L'Hopital's.
Which, yeah, effectively, it's quite similar. 1 over 1 minus 1 over 3 to the n. And where does that guy go? Goes to 1. And is 1 bigger than 0? Yes.
But only by 1.
Only by 1, but it's bigger than 0. Okay, so is picking out the things okay? One of them is the terms of your series, right? The other one is the thing you're going to compare to. Is the limit okay? Okay, just make a conclusion now. So, by the limit comparison test, the sum n equals 1 to infinity, 1 over 3 to the n minus 1, converges as this guy is a convergent geometric series. With r equal to 1/3. Technically, on almost every single problem in this section, you could just use this test and like not actually use direct comparison.
So you say that it's because 1 over 3 is a convergent geometric series and not because the limit equals some real number?
Well, that's the problem. All those things are necessary, right? So because the limit is finite, yeah, but the whole by the limit comparison test, like stating that is using the fact that this is bigger than 0. So Professor Fodry wrote in her note, the limit comparison test implies blah. But yeah, same idea. But if that number had not been positive, you just couldn't apply the limit comparison test. But it's always gonna come up be positive as long as you pick the right things. But what's the limit comparison? The implication is that if you do this limit and get a finite positive number, well then your series will converge if the thing you compared to converged, or vice versa with diverge.
If you don't, then the answer is indeterminate. You don't know whether the function is converging or diverging.
Honestly, I've never tried this test and had it not work out. So if that happens to you, let me know, and you're probably is more likely that you're making a mistake in your limiting process than anything.
But you have to say the part about 1 over 3 to the n is a convergent geometric series with r equals 1/3. Like that's...
Yeah, that part you have to do because it's a little bit like how in the, like this part's what you're talking about, right? Because you have to explain why you know the thing you're comparing to is convergent. Does that make sense? And you could also do that you could say like, we're going to compare to blah in the beginning, which is a convergent blah. Does that make sense? You could also state that right away. You could say, we're going to compare to this, which I know converges because blank. And then just do the test and say, therefore, my series converges as well. Yep. There's lots of ways to do this right. Okay. So stuff like this crazy crap. Oh, man. Technically, I think I made a bit of a boo-boo here because I think when you plug in 1, you get a negative term, don't you? Officially. That's my fault. It doesn't actually matter. So what I'm going to do just to make it, let's make that a plus, okay? Just change it. It won't change the result. Is what you guys have in your paper? Yes? Okay. So holy moly, well, I challenge you to actually do comparison to something without the limit comparison test is much better. So when you're applying the limit comparison test, you can just look at the series and just keep the highest powers of the top and bottom for the thing you're going to compare to. So let's let a sub n be equal to the terms of our series we're given. And find b sub n using the highest powers of the numerator and denominator. So what's the numerator's highest power? N squared. What's the denominator's highest power? Okay, so n squared over n to the 5th which reduces to,
We have kept our constant multipliers.
you could also have kept your constant multipliers. The value you will get out for your limit will be different, but the conclusion will not be different.
But it doesn't really matter whether or not we keep it.
Nope, it doesn't matter. And once we get to the end, I can tell you how it would change things, okay? Okay, so we're gonna compare our series to the sum from n equals 1 to infinity 1 over n cubed, which is a what series?
It's a P series.
It's a convergent p-series.
How do we know that?
Integral test officially with p equal 3.
Yeah, we got it.
That's what was yesterday? Okay.
It was a little bit fuzzy.
Okay, now we're going to find the limit as n goes to infinity of an over bn. Okay, so a sub n is 2n squared plus 5 over 4n to the 5th plus n squared. And dividing by bn is the same as multiplying by its reciprocal, right? So we're going to make that n cubed over 1. And then you're going to distribute.
Can't you just cancel that n cubed with both terms in the denominator?
You could have also done that. Do you guys see what he was saying? There is a greatest common factor in the denominator, so you could have canceled some stuff. But it doesn't really matter for the limit, does it? Okay, so in terms of actually showing a little bit of work, you have to divide by n to the 5th, right?
So it looks like 1/2.
2 plus 5 over n squared over 4 plus blah, 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 1 over n cubed, which equals 1/2. Did you guys buy that? Okay, so to make a conclusion, by the limit comparison test, what does the series, well, we have two series here, so here's a shortcut. Say sum n equals 1 to infinity an. What does that do? Converge or diverge? Converges. And the reason being is that we compared it to a convergent p-series, right? And that also, that 1/2 was definitely bigger than 0. How would it have changed if you'd kept the coefficients?
You'd have had multiplied by 4 over 2, which would have canceled out
Yeah.
the 1/2.
Yeah, this would have been 1 over 2n cubed. Does that make sense? Like if you would have kept those coefficients, the 2 over 4? Then this would have instead, here, this would have been 2n cubed over 1, right? Which would have made that numerator into a 4. Does that make sense? Which would have made your limit equal to 1. I am 99.7% certain. That's a made-up number, but I'm pretty certain that if you keep the coefficients, you're always going to get the limit being 1 every time. Is that, so if you do that, you could just kind of check and see, did I do it right by getting 1? Okay.
So if on an exam you killed a kitten and used the limit test that we learned before, and just, where it's like it equals 0, the limit of the original thing equals 0, and you said that meant that it converged, which is not the correct thing to do,
That's bad.
what would happen to you on the test?
You might not get very much credit.
Okay.
Because that's kind of a that's kind of like a kitten killing mistake of series, right? The assumption that the terms going to 0 means the series converges is just not true. So that, I don't know. I usually am pretty harsh with that one. Because people can get it right in like a true-false setting, like because they drill it in their heads enough, but then they like lose it in practice. Does that make sense? Yeah. Okay. determine whether this thing converges or diverges. This is one of the very, very, very few examples where limit comparison fails. And the reason limit comparison fails is because that stupid sign.
It oscillates.
It oscillates, and so if you try to do like limit comparison with like 1 over 10 to the n, you're gonna have something that's like an oscillating thing in your limit, which doesn't exist either. So for this kind of stuff, when you have oscillation, you are gonna have to use direct comparison.
Should you just compare it to sine n over 10 to the n?
Even better, okay? But it's not so bad because sine is a bounded function. Do you know what I mean?
So it goes from -1 to 1.
We know that sine of n is in between -1 and 1, right?
Is that less than or equal to 1?
Yep, and bigger than, yep, they both should be. So, then do you buy this? 1 plus sine n over 10 to the n is less than or equal to 2 over 10 to the n. How did I get 2?
Because you just take the absolute value of sine.
I just said sine is, the biggest sine is 1, right? So, okay, we're certainly less than this. And we're also bigger than or equal to 0 on that end, aren't we?
Which would have been what the other half of sine would have done.
Uh-huh. So it's kind of like on the right, I plugged in the biggest possible value for sine, which is 1. On the left, I plugged in the smallest possible value for sine, which is -1, right? And the terms, the fact that there could be some of them being 0 is not really that important.
Wouldn't you then automatically be able to
Okay.
say that?
But this is direct comparison, right? Does that make sense? So since the sum 2 over 10 to the n from n equals 1 to infinity is a convergent geometric series with r equal to what? 1/10? We know the sum from n equals 1 to infinity, 1 plus sine n over 10 to the n converges by direct comparison. And I don't think you just explicitly state what a sub n and b sub n are in this case so much as you have to state the comparison inequality. Does that make sense? Bigger one converges, smaller one converges too, right? Okay. Alrighty. Ready for number 3? I meant number 6. So this one, I don't want to run through all the, actually, I think you should run through the details because you can do this. So we'll pick out the series, the thing to compare to together, and then we'll go from there. So before you figure out what to compare to, what do you think you're going to do to that denominator? Distribute it out, yep. So this is the same thing as the sum from n equals 1 to infinity, 5 plus 2n over 1 plus 2n squared plus n to the 4th.
And when we compare that to just the highest powers?
Yes, so if you're comparing it to just the highest powers, what are you going to use?
2 and an n to the 4th.
Uh-huh, and the 2 doesn't matter, right? So we'll just say n over n to the 4th, which is 1 over n cubed, right? Okay, now I'd like you guys to find the limit as n goes to infinity of an over bn, like as in, I'm gonna stop for a second, and you guys should do that. Like I'll pass back quizzes to people who weren't here right on time. Okay, turn on. spoken here today? No aid, dishonor on them, no justice. You see him, Jaden, being up. No Joseph. Fell asleep real good. Okay. Morning. I don't judge, I fell asleep too.
And the limit equals 2.
Yeah, you should get the limit equal to 2. Did anybody else get that yet, or are you still working? Okay, that's fine.
Sorry, spoiler alert.
So yeah, spoiler alert, limit is 2. No, I didn't want to know that. Did you guys believe me when I told you that you really couldn't forget Calculus 1 at the beginning of the class? Or were you hoping that I was like lying? Just a little? But do you see that, like, you did find these limits in Calc 1, didn't you? Like things like this? Okay, so yeah, I got the limit was 2.
What you really can't forget is trig.
That too.
You forget that, it really bites you.
Okay, so since the sum from n equals 1 to infinity of Bn converges, and just like, you could even put in parentheses why that happens. What kind of series is it? What's the name for it? It's a P series, And what's the P equal to? 3. The sum from n equals 1 to infinity of An also converges by the limit comparison test. It is totally fine to use An and Bn in there. I would like to, because you define what they were above. Can I write something that's students always do wrong and it makes me want to cry?
Say like that was so.
Yep. So why is that wrong? Someone said it. Say it again.
That applies to the direct comparison test.
What did they do? An, if you don't put the sum symbol, what are these things? They're sequences. Do you see what I'm saying? So you really should put in the sum symbol, and you probably should also say where it starts and ends, because they don't always begin and end in the same place. Does that make sense? But at least writing A sub n and B sub n will save your poor, tired hands some writing time, right? Okay.
Well, especially when you have like 18 different pieces to it.
All right, this guy's a little bit more tricky because of the whole root thing. Yeah.
I just have a question on the last one. Right, P series,
You have to tell me why the thing you're comparing to converges. So that's why, that's like the little explanation as to why the thing you're comparing to converges, like why you know.
This is exactly the example of why you like the A sub n, B sub n thing.
Yeah, because this just like is ridiculously long. Okay. So, comparison here. So here, when you're looking at the highest powers, you have to also take the root into account.
So the highest powers would be like half whatever the highest power is.
Yeah, so the highest power on the top is still n squared. In the bottom, it's root of n to the 6th, which works out to be n to the 3rd, right? And then n squared over n to the 3rd is 1 over n.
Doesn't 1 over n diverge?
When you do the sum of it, yes. Okay. And then find the limit as n goes to infinity, an over bn. I'm sorry. Times n over 1.
stage 2 is it's super long term, you just leave things out.
Although, as long as you keep the highest powers, you're not gonna be wrong. Yeah.
Direct comparison test.
Good luck proving the inequality. So, I mean, you'd have to prove that AN is less than BN, and I don't know, I don't think that would, you can kind of use cross multiplication to do that, but it's disgusting. So it really isn't easier. And so that's the thing that Professor Fodry was saying, and I'm saying too, is that you can't just say AN is less than BN, you must show me why. In this case, actually bigger. You must show that AN is bigger than BN. You've got to show me why, and that's not easy, and it might not even be true. Does that make sense? So only do direct comparison if it's totally easy, obvious that AN is bigger than BN, or vice versa.
You could do the cross multiplication, pull your hair out and die.
Nah, I trust me, you don't want to. Here, one thing. When you multiply by 1 over n cubed, the denominator is a bit special because you've got to put that thing inside of a square root, right? What happens when you put that thing inside of a square root?
Kitten dies.
1 over the 6.
It gets squared and becomes 1 over n to the 6th.
Okay.
So this thing squares to 1 over n to the 6th inside the root.
Oh, I thought you meant if you didn't modify it, I said again.
Oh, yeah. 1 over n squared, 1 over n, 2, and then inside the root becomes 1 over n to the 6th, 1 over n to the 4th, and 1. And like on your take-home quiz, you're going to have to show your steps in these limits and just show me you know how to do it right. So then that limit's equal to 2.
It's greater than 0.
Which is greater than 0. So as the sum from n equals 1 to infinity, 1 over n diverges, you could say it's a p-series with p equal to 1, or you could say that it was a harmonic series. That's also like, we know that that guy diverges. The sum from n equals 1 to infinity of an also diverges. Oh my gosh, yeah. By the limit comp test.